All right, we're ready to do a few more Laplace transforms. So what I want to do next is I want to talk about how to take, there's a few different transformations. So I want to talk about a few of these. So the first thing I want to talk about is multiplying a function f by an exponential e to the at. And I just want to see what happens to the Fourier transform of this function. Remember that I think this is just worthwhile to have here. Let me just add this in, that the Laplace transform of f is the integral from 0 to infinity of e to the negative st f of t dt. And it's occasionally useful, and it will be here, to think of this as a function of s. So we write this as capital F of s. And so we want to compute the Laplace transform of e to the at times f of t. And what this means is that we're just going to apply the definition and see what happens. So this is going to be the first transformation. So multiplying in the argument of the Laplace transform, multiplying by an exponential. And so we're going to get e to the negative st, e to the at, f of t dt. This is really for any function f where the Laplace transform is defined. And it turns out that I can combine the exponential terms. So this is really just a one or two step process here, but I can combine the exponential terms to be e to the negative quantity s minus a t, f of t dt. Okay, because again, if you distribute the negative, you get negative st and plus a t. And so that's what we have. That's what we have up here. And this is nothing more than whatever the Fourier transform of our function was, shifted by a. Right? This is really capital F of s minus a. So this is what the multiplying the argument of the Laplace transform by e to the at does, is it really just shifts the Fourier transform by a factor of a. So if we multiply by e to the at, the output shifted by a. So for example, let's just remember a few of our favorite functions that we have. We know that the Laplace transform of cosine of kt, right? We know cosine of kt is going to be s over s squared plus k squared. So if I take the Laplace transform of e to the at cosine of kt, before I write it, think about what's going to happen. Okay, so think about what does it mean to shift this Laplace transform by a. Well, what it means is wherever there was an s, we're going to put an s minus a. So this is going to end up being s minus a over s minus a squared plus k squared. So, for example, if I were to take the Laplace transform of e to the 7t cosine of 3t, what would we get? What's going to happen? We're going to end up with, you should always just go back and think about what happens to cosine of 3t. Well, that's going to be s over s squared plus 3 squared. So that's s over s squared plus 9. And what we're going to do is I'm going to replace all the s's by s minus 7. So it's going to be s minus 7 over s minus 7 squared plus 3 squared. And so that's going to be the Laplace transform of e to the 7t cosine of 3t. Okay, so that's how that works in practice. Let's just talk about a few of the other ones. If we were to have e to the at times t to the 6th, remember that the Laplace transform, it's just helpful to remember, the Laplace transform of t to the n is n factorial over s to the n plus 1. Remember that this is really best viewed as gamma of n plus 1 over s to the n plus 1. And so what that means is that the Laplace transform of t to the 6 is going to be 6 factorial, so that's 720, over s to the 7. So that's 6 factorial over s to the 7. This e to the at I meant to write as in actual e to the 8t. And so what we're going to do is we're going to take our transform for t to the 6th, which we found, and I'm going to replace all the s's with s minus 8s, and we're done. So we're going to end up with 6 factorial over s minus 8 to the 7. Okay, so that's how that works. In general, I think it's just worth pointing out the Laplace transform of e to the at times, I need to pick something else, but let's say e to the at times t to the n, or t to the, let's say t to the beta, because I don't really care if the exponent is an integer or not. This is going to be the same formula because we know all about the gamma function. So e to the at is going to be t to the beta. It's going to be the transform of that. So that's going to be, I always just find it helpful to write it out. The Laplace transform of t to the beta is gamma of beta plus 1 all over s to the beta plus 1. So that means that e to the at times t to the beta is going to be gamma of beta plus 1 all over the quantity s minus a to the beta plus 1. Okay, and so that's how that's going to work for exponentials. And then just a few more. We know a few things. By the way, I should mention that if you think about the Laplace transform of e to the, say, 5t, we know what that is, right? We talked about the formula. This is 1 over s minus 5. But I can also think of this as the Laplace transform of e to the 5t times 1. And so what I can do is I can take the Laplace transform of 1, which you know is 1 over s, and then I can transform it by shifting it by 5. So this is 1 over s, where s has been shifted by 5, and we recover the usual 1 over s minus 5 that we knew however many videos ago. Okay, so this is how we do transforms exponentials. The last thing I want to just talk about real quick is let's evaluate the inverse Laplace transform of, say, 4 over s minus 3 squared plus 25. So what I want to do is I want to think about what is the inverse Laplace transform of this quantity. And if it was 4 over s squared plus 25, what we can do is we can think of this as, there's a nice way to unshift this if you think about this. Let me say this a slightly different way. If I were to have s minus 3, that means that we originally had an e to the 3t. So I can think of that as e to the 3t times the Laplace transform of the unshifted version, 4 over s squared plus 25. And now how do we find the inverse Laplace transform of 4 over s squared plus 25? Well, that's looking a lot like sine, except that would be 5 over s squared plus 25. So what we're going to do is I'm going to bring out the 4, and I'm going to put in a 5. Now we're not allowed to just put in a 5. In order to keep it balanced, this, by the way, is a 5. Back to having a problem with my handwriting here. This is a 5. So what we're going to do, let me try and fix this here. What we're going to do is we're going to put in that 5 at the cost of bringing another 5 outside. So I'm multiplying by 5 and dividing by 5. And now everything is fine. So it turns out that this is 4/5 e to the 3t times, let's see, the Laplace transform of 5 over s squared plus 25 is sine of 5t. Okay? And actually just one more here. So something that just occurred to me that we should talk about. Let's evaluate the inverse Laplace transform of s plus 3 over, let's say, s plus 2 squared plus 36. Okay, so let's think about how could we deal with something like that. Okay, so we have s plus 3 over s plus 2 quantity squared plus 36. Okay, this is all in the bracket, by the way. Okay. What we need to do is let's think about it this way. I'm going to shift this so what I'm going to do is I'm going to manipulate the inside. I'm going to write this as s plus 2 plus 1 over s plus 2 squared plus 36 plus 1 over the quantity s plus 2 squared plus 36. And the first part, we know how to undo. That looks a lot like cosine, just shifted by e to the negative 2t. And s over s squared plus 36 is going to turn out to be cosine of 6t. And for the second one, if it was a 6 over s plus 2 squared plus 36, then we would be fine. So we'll make it a 6. Okay, so what we can do is we can put a 1 over 6 out front, and then a 6 up top, and then we've balanced everything. Everything's fine. And we're going to end up with 1 over 6 times, let's see, we have e to the negative 2t because it's still shifted, sine of 6t. Okay, so that's how multiplying by an exponential shifts the Laplace transform.